Okay, so next talk about the graph convolutional network, GCN is model. So in the GCN, we try to learn the representation for all the nodes inside the graph data. We try to learn the embedded vectors. So for all the nodes inside the input graph, we can learn the representation simultaneously with the GCN model. So to build a GCN, we have to define a very important operator, which will be used in the GCN for constructing the GCN model. It's called a special graph convolution operator, or SGC operator by short. So this SGC operator tries to integrate the information from the nearby nodes, for learning the representation of the nodes, layer by layer. In this page, we show you with the example. Let's assume we have an input graph like this one on the left-hand side. Inside this graph, we have so many different nodes. Let's assume we are trying to learn the embedding vector for the A node as shown here. We try to integrate all the information from the graph to learn its representations. So in the SGC operator, they try to integrate all the information from the nearby neighbors of this A node, actually, to learn the representations. So according to the graph structure, surrounding this A node, we have several other nodes like B, C, D, E, F. They are all the surrounding neighborhood of this A node, right, as shown here, according to the connection among them. So when we try to learn the embedding vector for the A node, this representation for the A node, we try to integrate all the information from the nearby, these neighbors, and for integrating the information to learn or to update the A's representations. Now, how can we learn the A's representation? So we can learn the A's representation via a neural net. So we can learn the A's representation as HA as shown here, which will be a hidden vector, right, or hidden representation of the A node. And we can learn its representation by a model. It's called NN as shown here. It's a neural net. We will show the internal architecture of this NN, this block as shown here in the following pages. So this NN will receive multiple inputs. It will receive all the neighborhood information, surrounding this A node. According to the graph structure, this A, surrounding A, we have several other neighborhood, B, C, D, E, F, right? So therefore, this black box will receive inputs from all these nodes. The input will be their hidden vector as well. In other words, this NN will receive the HB, which will be the embedding vector for B nodes, HC, the embedding vector for C nodes, and so forth, and the embedding vector for F nodes as shown here. In other words, for learning the A's hidden representation, we have to receive the hidden representation of all the other nodes, their embedding vector as input for updating the A's representation. Then you may wonder, how can we define the HB, this B's representation? Is a B's representation can also be defined by the NN, this model. It will further receive the inputs of the nearby nodes surrounding B node as well. So surrounding B nodes, we have several other nodes like this one, and A as well. In other words, to define its HB, it will receive inputs from the other nodes surrounding B as well, for defining its representation, and similar for the other nodes. So you can see, to learn the representation for a node, we have to integrate all the surrounding neighborhood representation together. Then we can further define the representation for the target node. So this SGC operator will integrate all the surrounding neighborhood inside input graph for learning the representation for the node and for a target node inside the graph. So this gray box will be used with multiple layers depending on how deep this model will be. If this model architecture has another 2 depths, then we will have 2 layers of this operator as defined here. So in this way, we can define the representation for the target node A as shown here. And you may also wonder, because inside the input graph we have so many different nodes, right? We have so many different nodes. Then, how about the nodes representation for B, C, D, E, F as shown here? Actually, this operator we use to apply to all the nodes inside the graph. We apply this operator to the A's node as a target node by integrating its neighborhood and so forth, right? And when we try to treat this B as a target node, we will also define a similar architecture for learning its representation as well. We show you the architecture for the learning representation for other nodes in this page. So depending on the target node, we will build a very similar architecture as shown here, right, to learn their representations. So by integrating the neighborhood representation, we can learn all the nodes representation layer by layer, iteratively, also simultaneously. We can learn the representation for the A's node, for the D's node, and for the C's node as shown in this page, and similar for the other nodes. They all rely on their neighborhood representations, and we try to integrate all the neighborhood representation together for define the target node representation layer by layer. You may also wonder what will be inside the gray box for the NN for defining this operator. We will show you the architecture inside the gray box in the following page. So we have shown you with some high-level idea for learning the representation for a target node already in the previous page. Then we wonder, how can we use this architecture for learning the representation layer by layer for all the nodes? So we show you the internal architecture for the NN gray box in this page. So before we take a look at this N and this gray box, let's have a look at the formula we show on the left-hand side. We know that in the deep learning, we have to initialize many of the terms inside this model architecture, right? We will use this H to denote the embedding vector for the nodes inside the input graph. So now here we have HA denoting the embedding vector for A, and here we have 0, as a superscript denoting this one is the initialization for the embedding vector for the nodes. And we can initialize this embedding vector for the nodes as XA as shown here, as this is raw feature vector input. Also, according to the previous discussion, we know that we can update the A's representation or the embedding vector of A layer by layer, right? Now here, if we are considering this A as the target node at the case layer of the model, then we try to update the A's representation at the case layer by the SGC operator we defined before, right? Then by the gray box that we show here. And you wonder what will be inside this gray box and how can we define the gray box as shown here. We define the gray box as shown here by the formula in this page. We mentioned that we will try to integrate all the representation of the surrounding neighborhood of the target node, right? To update its representation. So here we have this gamma A denoting the neighborhood of A node inside this input graph structure. And we try to enumerate all the nodes inside the neighborhood of A, and we can further integrate all their representations. Because here we are learning the embedding vector for the case layer, and we already know their representation at the node layer in the k-1 layer already, right? Therefore, by integrating their node layer representations together, surrounding the target node A, we can learn the representation of the A at the case layer according to the formula. So we try to sum them together according to the formula. We sum all the neighborhood of the A's node inside this input graph structure according to the representation we learn at the node layer. Also for the neighborhood node V, for example, instead of directly summing them representation together, we also try to assign them with a weight. The weight we assign with them is 1 over the size of the neighborhood size of V vector. Because for this V vector, it will be connected to multiple nodes, right? Depending on the numbers of nodes it will be connected to, they will send out one portion of its information to the neighborhood, right? Though, for example, if this V is connected to multiple nodes, in other words, gamma V, this set will be very large. Then the role for this node V to play in the integration process by formula will be a small number, right? So therefore, we assign the information we can integrate from this node by a weight. The weight is defined based on the degree of a node inside the input graph structure. So therefore, we have a weight 1 over the gamma V set size as shown here as a weight. So of course, this is the integration of all the neighborhood information or the representations, right? And we try to further utilize this term to define the representation for the A node as the target node. So given the vector representation, we sum here, and we also want to update it according to a weight, according to some variables. So we define W1 as a variable for updating the integrated of information from the neighborhood nodes. And besides the neighborhood information, the A node will also receive information from the A itself from the node layer as well. Or we also sum this HA k-1, the node layers of its representation, and sum them to the neighborhood information as well. And its information will be updated by the W2, this variable as shown here, to be learned. So W1 and W2, they are the variable to be learned inside the model architecture for defining the NN layer or the SGC operator. And inside the component, we will integrate all the neighborhood information we show here, right? Now B, C, D, E, F, they are the neighbors of the A node, and we'll sum them together, sum their representation together from the node layer. And for different neighbors, we assign them with different weights, which is denoting the degree of the corresponding neighborhood nodes, now B, C, D, E, F, right? So by summing them together, the neighborhood information together with the A node itself is information, then we can further define the A's representation at the case layer by the formula we show here. Here we have a sigma denoting the activation function. This denoting the representation we can learn for the A's node at the case layer, and we can do this iteratively with multiple layers, like capital K layers. And the representation we can learn, we can compute for the final layer of this model, then we can denote them as a final learned representation of the target node A. So this process will be done for all the nodes inside the graph structure simultaneously. So this is for one single node, right? And we also wonder if we plan to learn all the nodes representation simultaneously, and how can we denote the learning process? So if we try to learn all the nodes representation inside the input graph, we can denote their embedding vectors or their representation vectors as a matrix. We organize all the nodes representation into a matrix as H. I mean the capital H as shown here. This will be a matrix. The size of this capital H, denoting the representation we learn for all the nodes inside the graph. In other words, we're stacking all these lowercase h vector for all the nodes inside the graph together to define the H matrix as shown here. Right? This DH denoting the dimension for the H vector we show here. Right? So therefore, this H matrix will cover all the nodes representations inside the input graph. Then we can further rewrite the formula we show here to define the H vectors. Inside the definition for the formula, we define this H vector by integrating all the information from its neighborhood. Right? Or the integrate itself into representation from the lower layers. Therefore, to define or to rewrite this formula, by integrating all the nodes together, we can simplify the formula we show above as a very simple formula we show at the bottom part. Here we have this summation for all the neighborhood. Actually, this neighborhood information can be indicated by the adjacency matrix of the graph effectively, right? Either we integrate who and who are connected together to each other by the adjacency matrix. So, for the formula we write here, it covers, both A hat denoting the normalization version of the adjacency matrix of the graph. And we have HK-1 denoting the lower layer representation covering all the nodes inside the graph. And we also have the parameter or the variable W as shown here. And here, if we assign W1 and W2, they have a shared weight, then we can simplify this W1 and W2 into one single variable as W as shown here. So the tricky part for the formula will be about the A hat. This is A hat denoting the normalization version of the graph. The main reason is because for the term with sum here, we have assigned them with a weight which is penalized by degree of the node V, right, for each node inside this neighborhood gamma A. And this will be a penalized term. In other words, in the integration, this term will be normalized, right? Therefore, that's the reason why we also normalize A matrix by the degree matrix, the corresponding degree matrix of this A matrix. Also, in the formula, besides the neighborhood information, we also integrated the A itself information, right, inside the formula. Therefore, besides the adjacency matrix, we also added it with this I matrix, denoting this identity matrix. So it's denoting the diagonal matrix, the degree matrix of the nodes inside the graph. So by times matrix A plus 1 with degree matrix as shown here, we can normalize all the entries inside the matrix. Then we can use this A hat inside the formula. So therefore, all the updating process inside a graph can be denoted by the simple formula we show at the bottom. We have A hat denoting the normalized adjacency matrix times it with HK-1 times with W variables. And then we can further feed them to a sigma function for the activation, and we can return the result as HK to be the representation we can learn at the case level. So based on this H0 for all the nodes, we can learn the representation for all the nodes inside the graph layer by layer from K equals to 1 until K equals to the capital K. And all the representation we can learn from the final layer will be returned as the representation for all the nodes. So this is the process we learn the representation for all the nodes inside the graphs based on the K SGC operating layers. So by stacking multiple SGC operating layers on top of each other, then we can define the model to be the GCM model, the graph convolutional net model.